7, 5, part 2, matrix multiplication. So another operation we can perform is matrix multiplication. It's different from scalar because when we have scalar, we're just taking every entry and multiplying by a number. This time with matrix multiplication, we're going to do something a little bit different. We're going to multiply using this row and column multiplication, where we're going to take the rows in the first matrix and multiply them by the numbers in the column of the second matrix. And then we'll be adding different parts together. So you'll see as we kind of work this through. But what's going to happen is I'm going to take everything in this row, multiply each of those terms by everything in this column, and add them together. So it'll be the first term times the first term plus the second times the second plus the third times the third plus, and so on. And I'm going to need to do that for every row and column grouping. So let's take a look at this example. So we have these two, we want to multiply A times B. So to find the product AB, what we need to do is multiply -1, 4, 5, 3, -2, 0. Multiply this times this. Whoops, not so big. -3, 2, -4, 1. Okay, so what's going to happen is we're going to start with the first row in matrix A. And we're going to multiply that by the things in the first column. So we're going to do -1 times -3 plus 3 times -4. And that's going to give me my first entry. All right, the next thing I'm going to do is the second row with the first column. So that's 4 times -3 plus -2 times -4. Then I'm going to do the last row with the first column. That's 5 times -3 plus 0 times -4. All right, so the next thing I'm going to do is start back again with the top row, but the second column. So that's going to give me row 1, column 2. That's -1 times 2 plus 3 times 1. All right. Row 2, column 2. So we're going to do 4 times 2 plus -2 times 1. And then lastly, we're going to do row 3 times column 2. So that's going to give us 5 times 2 plus 0 times 1. And let's just figure out that arithmetic real quick. Let's see, that's 3 and -12, so -9. That's -12 and +8. So what are we at? -4, -15 and 0, -2 and 3, 8 and -2, and 10 and 0. Okay? So what you want to make sure is when you are multiplying your matrices, you want to make sure that matrix 1 has the same number of columns as there are rows in matrix 2. Okay? So first matrix, number of columns needs to equal second matrix, number of rows. If that is not the case, it would be undefined because we wouldn't have anything to match up to multiply. Okay. Then we have the definition of an identity matrix. So if you think back to Algebra 1, when we used an identity, what it did was if I multiplied by the identity, so the identity for addition would be, for regular numbers would be 1. If I multiply by the identity, it does not change it. So this is going to be a matrix that I can multiply by that does not change it. So if I take matrix A times the identity matrix I, it should still give us matrix A. It should give us something equivalent. It shouldn't make a difference. Now that identity matrix is actually in row echelon form, and what that's generally going to look like is a bunch of 1s and 0s. So that an n by n matrix, so basically a square matrix where the number of columns and the number of rows is the same, consists of 1s on the main diagonal, okay, and 0s everywhere else, and that makes it a identity matrix. So again, we noted that it is square. Sometimes you'll find that we write I with a little sub n, or just I. I is a little bit easier. So if A is an n by n matrix, then the identity matrix has this property that if I multiply by the identity, it should not change it at all. Okay? So I took some random matrix and I multiplied it by the identity, and it's the same size. Notice there's 3 and 3 here. and I should get the same answer no matter what order I multiply in.